Hello, good evening. Can you hear me? Okay, so let's start today's session. This is the 8th assignment and last session. Then we will wrap up all assignment tomorrow, same time. So let's start. First, discuss the purpose of the course and motivation, and then material. We discussed, I think, sir, discuss renewable, non-renewable energy sources, non-renewable, renewable, non-renewable. They are limited in nature and also pollute the environment. So solution is renewable energy. We can use three again: wind, hydropower, solar, geothermal, and biomass. But solar can easily exist everywhere. Where is the sunlight? So we know the So, sunlight is abundant on Earth, so we can easily use with the help of solar photovoltaic. These are the worldwide we have fourth number and uses, and this is the low maintenance. Also, we can see many application sustainable also. So we can see one by one chart efficiency single junction solar cells is this is reference to air with respect to the efficiency how goes. So you can see in chart efficiency goes up day by day. All technology are mature, then efficiency is get higher and higher. Multi junction you can see also. Then crystalline silicon solar cell and thin film technology. Then emerging technologies perovskite and so this lecture about perovskite and thin film technology we will discuss in upcoming. So let this is the first question after the intro. The oxide that can be used as a transparent conducting electrode in solar cell. Please answer your question. Okay, so transparent oxide, which oxide that can be used as a transparent conducting electrode in solar cell? So answer is indium doped tin oxide. This is ITO. Fluorine doped tin oxide FTO. Aluminum doped zinc oxide. So these are, so we are generally use FTO or ITO. Also people use aluminum doped zinc oxide, sorry. So this material has higher band gap. So light can is pass through these. Let's say this is our FTO ITO. This is sunlight. Then let's say Next layer is absorber material, or ETL STL might be there. Okay, so this is the people generally use because they have higher band gap. Light can easily pass through this. Next question is, read the question. Question is, which of the following is are required for exciton dissociation in single junction organic solar cell? So your answer A and C. So let's check. A and C, your answer is correct. Which of the following is are required for the exciton dissociation in single presence of interfaces and presence of electric field in the device? Okay, your answer is correct. So let's move for next question. The primary light absorb material used in perovskite solar cell is a primary. Choose your options. Perovskite. Perovskite has a BX3 like structure. X can be generally halide, chlorine, bromine, or oxides. Sorry. So this is, let me tell you, this is the perovskite structure. Perovskite has a CS3 NH3. This is A part, and PP is metallic B, and so A. I3 is like ABX3. So this is the primary material, and band gap 1.55 eV around. Perovskite, this methyl ammonium lead iodide MAPI. Okay, so primary material is this. Perovskite should be material band gap nearer to the, we know the band gap versus efficiency. So maximum is around 1.34 eV. So nearest look like that chart efficiency. we know. So if material closer to the optimum band gap is better for any solar cell, good solar cell, because give maximum efficiency. Next, which of the properties perovskite material is are beneficial for their use in solar cells? So the structure we know ABX3, but which property is following properties is are beneficial? Why is use ABX3 material for solar cell? Which property is good for solar cell? Let me just question you. I want to make solar cell. For this, which in this option, please choose the for good solar cell, which property should be. Let's forget about perovskite. Then we will discuss perovskite. B and C. Okay. Obvious low defect density. Good. C high absorption coefficient. And what about the charge carrier diffusion length? E. If let's say charge carrier is goes to head and material thickness that much, let's say T, and diffusion length is L, electron and hole, they can easily recombine. Charge carrier diffusion length should be high, otherwise they can recombine within the material also. So long charge carrier diffusion length should be. Perovskite has good solar cell, you are right. Let's say low defect should be. High absorption coefficient should be. Second, third, high carrier movability also should be, and high diffusion length and charge carrier lifetime should be high. Charge carrier lifetime should be high, and also should be stable in ambient condition. Long survive, like silicon has lifetime is 25 years, should be like that. Clear? But perovskite has in this given option has high absorption coefficient and long charge carrier diffusion length. We will discuss in upcoming slides. Let me tell you. Perovskite has like structure. You can see A is goes to here This is A part, and B you can see in the octahedra center, tetrahedra. Sorry, here like that. This is B. A corner sharing as halogen part. Okay, so this is stoichiometry ABX3. A can be organic, inorganic cation, inorganic CSK, and organic this. B is metal. We can see lead, tin, G. X halide and anion can be like bromine, hydrogen, and chlorine. Example MAPI, we have already CS3 and H3 PbI3. We have to discuss one question on primary absorber. Also, this FFPbI3, this is FFPbI3, and for perovskite, alpha should be 0.81 to 1 for cubic perovskite. So this is the tolerance factor Ra plus Rx divided by root 2 Rb into Rx. And property you can say high absorption coefficient, high carrier movability. Perovskite has high diffusion length, high charge carrier lifetime, super power converter efficiency. And we can also tune the band gap of perovskite changing by a halide part, chlorine, bromine to iodine. Bromine has, let's say Br, if you use Br halide part, has a higher band gap. Small halogen give larger the band gap, and if we move higher to the cation, sorry anion, band gap will reduce. So we can tune the band gap. So we can also tune the band gap of perovskite. Compatibility with the solution and vacuum fabrication method also has a low production cost. So these are superb properties of perovskites. That's why this is around 26% or higher efficiency of solution process based perovskite. Compete or comparable with silicon, but silicon has a higher cost, but our perovskite has low cost. But issue is this: lifetime is around 1 year, and silicon has 20 to 25 year. So people are working on this gap, improving the lifetime of solar cell perovskite. And due to the tunable band gap, people use this perovskite solar cell with another solar cell to make the tandem. So with tandem, this is commercialized. Perovskite solar cell with tandem is commercialized. Single junction is not commercialized because as a lifetime is 1 year. So whole scientific community which working on solar cells are working on this stability issue. Okay, so if you want to how perovskite is work, let's see. This is different from the perovskite has a, let's say, MAPI. This is perovskite material, you can see. Okay, then has a, if electron and hole is centered in this absorber layer, they are separated. Electron transferred by SNO2 and hole transferred by a hole transport layer. This is called HTL, ETL. Electron transport layer, hole transport layer to the metal contact. This is FTO. So sunlight B sunlight goes from the FTO to SNO2. These are higher band gap, so doesn't absorb. So absorber MAPI has perovskite MAPI absorb the sunlight with respect to the band gap, and exciton MAC and dissociate and electron hole pair are generated. They are transfer. So let's check how these are the this is electron transport layer. So these are conduction band and these are valence band, and this is metal. So with respect to the vacuum, this work function. Okay, so let's see, this is sunlight is coming from FTO or ITO side. Then this is our perovskite, electron hole pair, exciton are excited, then electron hole pair are generated, and electron in the conduction band, hole in the valence band, and electron goes via electron transport layer because energy is minimum. Electron don't go this side because energy has conduction band has higher energy for electron, and we can see with respect to whole energy electron energy is higher this side, but in the case of whole energy is increasing in this side. So this is lower energy of for whole. So whole goes from here to here to the STL layer. Don't go because it has a higher energy. Then transport to the contact, metal contact, or FTO or ITO electrode, then collect by external circuit. Then we can measure the current and voltage to get IV. This is for dark without the light, sunlight, but we illuminate a solar cell in the presence of light, then this whole spectrum is shifted to the downward. Okay, so you know process for first is light absorption, exciton, electron, excitons of electrons, generation of electron hole pair, transport charge carrier, and charge collection. These are the major steps. So this is the process. Okay, clear how perovskite solar cell is work? Any doubt? Sorry. If has any doubt, you can ask. So this is FFS. You can see this chart band gap with respect to the current and efficiency. So SQ limit and near is FAPI based perovskite, FA based perovskite. SQ limit. This is around 33. We can get 30, then low and low. Okay, so this is with respect to the band gap. We can single junction, we can get maximum efficiency like that. 10, 20, 30, 33 is maximum. Also the current density. So FA base sorry, perovskite is used because can give maximum efficiency near to the SQ limit and also has high time. This MA has easily degraded to convert to delta phase in the presence of the high temperature, but FAPI better long-term thermal stability due to the higher activation energy of the thermal. So also has an advantage FA base. So this is perovskite, about the perovskite. You can see the comparison with silicon. Cost as half of the silicon. Efficiency, this is old chart, around 26.7% nowadays, and but we are lacking here. So research committee overcome degradation for 1 year only lifetime. So work can improve via encapsulation, additive incorporation, modification of charge carrier transport, composition engineering like BX3 can mix A and A or replace MAFI FAFI, can use intermix of some percentage. People are working in these areas. Implementation of double metal electrode, dimension engineering. These are the options to improve the lifetime. 1 year to we want to around 10 to 20, 10 to 20 year. Then can commercialize. All properties are good except the lifetime with respect to the silicon, and cost as you can see half of the silicon. Okay, so fabrication, you can also see how can we perovskite is made. First, FTO right to sheet we can take, then we can easily spin coat. If we have solution, take the solution, then spin coat. Spin coat means we have substrate like that, and the motor, this is rotate 4000 to 3000 rpm, spinning, then solution drip, then spread pin film or foam, also the perovskite, then then will transport layer. Sorry. So then vacuum deposition, ultra high vacuum deposition of the electrodes. So this is the laboratory process. How can we can make the perovskite solar cell? Clear? And perovskite has PIN and IP structure. PIN means with respect to the light. If this is sorry, this is NIP, this is PIN. Whole transport, so this is called p-type layer, this is intrinsic layer perovskite, and for this is electron, so this is N. So with respect to light, PIN, and similarly this is for N, this is intrinsic, this is for whole. So these two type architecture are generally used. Also mesoporous some, but this is NIP and PIN, the architecture for perovskite. So we will discuss the characterization after some in last, but first is let's discuss the questions. Then we will discuss the characterization, the last. The reason for using soda lime glass as a substrate in the fabrication of copper indium gallium selenide solar cell is please choose your option. Give me 1 minute, I will come back. Please think about this question. So your answer is B and C. So good, your answer is correct. B and C. Sodium helps in surface passivation and sodium improve the film texturing. Okay, so that's why soda lime glass as a substrate in the fabrication copper indium selenide solar cell are huge. You can see from the lecture. Lime glass. Sodium helps the surface passivation, and alpha matches with the CIGS solar cell. Okay, so glass size is 1 micrometer and composition sharp slides from the surface to bulk, decrease surface reconstruction, post annealing in selenide deposit on the sodium we have already discussed. Back contact, these are the this is the for device people or in lab post treatment as a sodium lime glass is used and surface passivation and film texture are improved with the help of sodium lime glass. Next, which of the following is our critical issues with the dye synthesis DSCC solar cell? Please choose your option. Any idea? So option B and D is use of liquid dye and electrolyte degradation. These are the critical issues. Dye synthesized solar cell you can see in this picture. Electrolyte. So electrolyte degrade. So this is the problem and also as a liquid dye. Another issue in DSCC dye synthesized solar cell. You can see the architecture of the DSCC. Please see in picture. TCO, then electrolyte, TiO2 dye, and TCO again, then glass below, and this is glass, in between TCO and electrolyte and dye are used. And thickness also you can see dye with 10 micrometer thick. And this is discovered by Michael Gratzel in 1985. Okay, so let's move for next question. Next question. Bulk heterojunction organic solar cells has superiority over bilayer organic solar cell due to. Please think about this and choose your options. Relative thinner absorber layer, better dissociation of excitons, better interfacial contact between donor and acceptor phases, lower optical absorption. Sorry. Okay, so your option B and C, yeah, correct. Bulk heterojunction organic solar cell, better dissociation of excitons, and better interfacial contact between donor and acceptor phases. This is taken from the lecture, you can see. Design of organic solar cell. Anode, electrode this side, and cathode, electrode, band gap 3.2 eV and 4.2. This is organic. So electric field which can use to break the excitons in this organic solar cell. Efficiency is less, but electrolyte, polymer electrolyte and glass determined by excitons diffusion length, small and low, smaller absorption. So this is the design, and bulk heterojunction organic solar cell has a superiority over the bilayer organic solar cell. So in the heterojunction organic solar cell has better dissociation excitons and also better contact between donor and acceptor phases, electron and hole, with respect to the bulk. Okay, next question. The starting source of the sulfur for the window layer deposition copper, indium, gallium, selenide solar cell is R. This is the question. Please choose your option if you have idea. Okay, A, you are right. So cadmium sulfide deposition can be deposited by chemical bath deposition (CVD). You know chemical bath deposition. Chemical are filled in the beaker and substrate, like where substrate dip in the chemical bath, like technique. Aqueous solution with so you can see source is the option. Okay, so this is the reaction. Temperature 80 to 60 degree will use, and source this is used. Cadmium sulfide NH2 NCN and 4NH3 into H2R MAC product will form. Okay, so let's go for next question. The photosynthesis used in the dye synthesized solar cells should be high conductivity or high electron conductivity or band gap. What about the band gap? Low and high. Photosynthesis used in DSCC solar cell. Why? Please think about this. Yes, please, your answer. So, reduce the band gap. Okay, why? Because low band gap. Only if band gap is higher than efficiency, we will compromise with the efficiency. So that's why should be the low band gap photosynthesis. Okay. Next question. Which of the following is used as a dopant in the polypropylene polypyrrole based organic solar cell? Yes, please choose your option. Okay, let's check. Yeah, you are right. You can see from the lecture dopant polypyrrole as a FeCl3 if polythiophene, then as SO3CF3 will use. And backbone, this is solar cell, organic of the electron device. This is polymer, easily can solution process, small molecule. Next question, let's see. The photoelectrode used in DSCC's dye synthesized solar cell is nano SNO2, platinum, nano ZNO, nano TiO2, NiO. Photoelectrode as a photoelectrode in DSCC. Which option is correct? Indeed. Let me check the answer. Also, the C, D is your right, but also ZNO. Give me a moment. Hello. हाँ वो तो चालू है मैं ऐसा तो बोल रहा हूँ So nano, so you can see photoelectrode, TiO2, and ZNO will use generally used for DSCC. Okay. Photoelectrode and photosynthesizer. You can see natural dye, Arubis dye, and polypyrrole dye composition. In lecture you have I think already seen. These are the reactions. Next question. Which of the following is true or not, sorry, not true for the organic semiconductors? These are the four options. Please see. They are indirect band gap semiconductor. They are direct band gap semiconductor, or radiative recombination is high in organic semiconductor. They have high exciton binding energy. Please think about this. Not true for organic semiconductor. Sorry. Yes, please choose your option. So they are indirect band gap. This is not true. And high exciton diffusion length. In organic solar cell, it is a problem. Low diffusion length, and but they are direct band gap, not indirect. Okay. Next, the band gap of the copper indium gallium selenide can be tuned by. These are the five options. Incorporation indium vacancy, increasing the thickness of copper gallium indium films, selenides film, varying in indium and gallium ratio, incorporation copper interstitials, incorporation indium interstitial. See, let me check answer. Yeah, you are right. Varying in the indium and gallium ratio. Then we can tune the band gap of copper indium selenide. But in perovskite, let me ask question. If the perovskite, then halide part is responsible for band gap variation. Band gap tuning. By halide. Next question. The p-type character of the copper indium selenide is attributed to the copper vacancy, selenium vacancy, gallium vacancy, copper interstitial, and indium vacancies. Okay, let me check. Yeah, you are right. Copper vacancies. 14. This is sorry. This is 15 question. The photoelectrode used in Dyson's solar cell is a. I think this is repeat. Sorry, photoelectrode in DSCC. We have already seen this question, so this is a repeated question. Okay, dopant added polythiophene it make to conductive is is this is 50. Before 15 is repeated, so this is the question. Please choose your answer. Okay. So the D is dopant to make it conductive. For conductive is I think we have already seen why this is added in previous question. Polythiophene. Let me go back. Where is yeah. So this side you can see thiophene. Okay, and FeCl3 polypyrrole. Last question is what is this? Last question. This is polythiophene. Okay, so this is dopant as a use. So let's discuss some characterization. How our perovskite film is good can we can determine. So characterization, X-ray based characterization, electron based characterization probes, tip based characterization, and UV visible infrared based probes. In XRD, the Q pattern material looks like 2 theta versus intensity like peak we will get in a specific angle. Okay, Then we can check the intensity, how much FWHM. So what is the peak width intensity, how much. So these are, we'll check for material. Our material is good or bad, how much is good, comparison also. So these are the characterization. X-ray base also UPS, XPS. UPS give the information of conduction band, sorry, valence band. XPS give the binding energy information, how bond are tightly bond or okay. XRA and XS, these are the X-ray base source, are X-ray base source will use and detect the signal, okay, and we will get the information about the from the signal. And electron base probe SAM and TEM, we can see the material surface structure, how look like. This is give the image, also the information about the grain boundaries, and the elemental analysis also we can get. Same in the time. This is more powerful, but material requirement of the material is different. Also the tip base, STM, KPFM, AFM, these are the and UV visible, FTIR, IS, MPS, TIS, UV visible, ellipsometry, photoluminescence. So PL generally and band gap from the UV visual top load give the material band gap, and PL give the information about the defects. And one peak like that we get around 800 for perovskite. Higher the peak, our material is the good and should be the sharper and higher the intensity. Then intermediate state and defects will be low. So this is the base how we can determine our material is good or bad. So this facility will use to know our material is what type of defects or what type is surface, what type of phase will form, what is the roughness, what is the bend gap, how the absorption. Okay, if you want to read, this is some information about the X-ray base absorption spectroscopy, XRA fluoro, beam induced current. So I will upload this slide, then please read this. Scanning electron, how is working and what will we get information. These are elaborate here about the time also. Scanning tunneling microscope, Kelvin probe microscope, impedance, Fourier transfer, FTIR, Raman spectroscopy, photoluminescence, PL, and transient absorption, TIS. Okay, so please read by yourself. I will upload this slide. For this is material characterization. Okay, Are you there? Okay. Yes, okay. So tomorrow also we will take 2 hour classes, wrap up the all the session, and if you have any doubt you can ask regard and think your exam is near. This is all about today's session. Okay, thank you and prepare your for your exam. Best of luck. Tomorrow we will. You are not getting same link and time same time same link. You can join by this link same link. Uh, I will. Okay, okay. Thank you. So same link will use for tomorrow's session also.